Yeah, so my screen is shared. Mic is unmuted. Okay. So, uh, welcome everyone. This is the discussion of week 12 course content, which was primarily based on heat exchangers. So, you know, uh, heat exchangers are like, from practical point of view, uh, this is the classical equipment or instrument where whatever we study in this course or in general with respect to heat transfer, in most of the practical applications it is essentially employed using an heat exchanger. For example, in class it was told that there are like different categories of heat exchangers. First is, there are direct contact heat exchangers where the fluids uh, heat interaction, amongst which heat interaction is happening, those fluids directly mix with each other. But in practice, direct heat exchangers are not that common. In some particular application, or very less number of applications are there. Most of the applications it will be indirect heat exchange, or indirect heat exchangers, which are also called as transmural heat exchangers. So uh, in that case, I mean, transmural is a synonym for indirect heat exchange, and in practical applications, you don't want the two fluids to mix in most of the cases. Therefore, that is the area where you'll see most of the applications will lie in. And then there are like uh, two types of indirect heat exchangers. First is called as single phase heat transfer, wherein both the heat interacting fluids or thermally interacting fluids, they will be in a single phase, whatever it is, liquid or gas. But then there are certain cases in which one of the fluids or both of them could be undergoing uh, phase change. Typically, from practical point of view, usually there is one fluid which is either undergoing condensation or evaporation. Typically, it is water, but there can be other fluids also. And the other, so that will be first fluid, and then the other fluid will be there, which will be either cooling it or taking the heat away, or giving heat to it for evaporation, or taking heat away from the condensing fluid during the condensation. And then there is geometrical classification, in which basically, what do you say, uh, like three categories of heat exchangers we typically study. This is geometric classification of heat exchangers. Uh, I'll be using this HX as the acronym for heat exchanger in this class, uh, just because it saves some time. Otherwise, every time you have to write heat exchanger. But just keep in mind that wherever I write HX in this class, it is heat exchanger. So there are three types basically which are practically or widely employed in practical applications. First is called as double pipe, and here we study like co-current or parallel flow heat exchangers, and then there are counter flow as the second category. Then there are shell and tube. Uh, Mostly in case of power plant, etc., you'll see shell and tube heat exchangers in boilers and even in condensers, etc. And then there is third category which is called as compact or miniature. Also, they are sometimes called, but typically compact is the correct word. So these are like uh, plate fin type of heat exchangers, and typically used for gases because otherwise the pressure drop for liquids is high when the width of the channel or the dimensions of the channel are small. So this is basic overall practical cases of, or practical geometries of heat exchangers. We'll take some problems amongst these only, uh, but in our problems it may not be dependent on geometry this much, but in practical applications, if you are doing higher studies or something, and if you want to design any experimental setup, then you have to look at the geometric classification also, so you should have some idea. Then there is something called as fouling. So what happens whenever there is a fluid flow, we usually try to maintain its purity, but you know in some or many practical applications, uh, you know typical demineralized water is also fine, but that also has some salt content, right? So over the period of time when you use the same water in a loop, or if you add some makeup water also, there will be some decomposition of dissolved salts onto the heat exchanger tubes or surfaces, and over the period of time that leads to scale formation, rust formation, and that adds thermal resistance in your heat transfer processes. So that is signified by fouling factor. So I think we have studied this uh, previously also when we studied conduction and convection heat transfer, and especially when you uh, study the thermal resistance network diagrams for the various geometries like slab or concentric cylinders or spheres. In that case, also you consider fouling factor as a one of the thermal resistances if it is significant. In the case of heat exchangers, it comes into play when you determine overall heat transfer coefficient. So here UI represent overall heat transfer coefficient, and UI means it is calculated based on the inner surface area of the heat exchanger tube or pipe, whatever it is. That changes according to your geometry, or one can define it based on the outer surface area also. And then you'll have resistance offered by the wall of the heat exchanger tube or pipe. Then there will be resistance offered by the fouling, thermal resistance we are talking. And then there will be usual uh, thermal convective thermal resistances because of the uh, convection of the fluid inside and outside the surface area of the tube. So and this typically from previous, we have studied this previously, how to calculate wall resistance depends on the geometry. Typically it will be concentric cylinder, so ln r2 by r1 divided by 2 pi k l, and this fouling factor is in some problems it is given, so you should know where to use the fouling factor. And in some cases, in some subjective questions also they ask. So typically with the periodic use or prolonged use of the heat exchanger, fouling starts to happen, and then the fouling factor, sometimes it may play a very critical role because it may be determining the overall heat transfer coefficient. Just give me 1 second. uh, 1 second. Yeah, sorry, I got something in between. So I think I'm still presenting only, right? 1 second. Yeah, so you have to consider fouling factor in some problems it is given. So yeah, because it affects your overall heat transfer coefficient. And yeah, there is a famous question, you know, like it is mostly like interview question because they will grill you on this if you answer it, even if you answer correctly. So the thing is, what they ask is for same inlet and outlet temperatures uh, with same uh, heat transfer area, let's say A, and overall heat transfer coefficient U. So basically everything is same, inlet outlet temperatures, area, overall heat transfer coefficients. Which heat exchanger will 1 second. Yeah, which heat exchanger will have better heat transfer, or you can call it superior heat transfer also. It doesn't matter. And this was discussed in the class also, that that LMTD, logarithmic mean temperature difference for counterflow heat exchanger, is greater than LMTD temperature difference for parallel flow, and therefore typically, you know, parallel people prefer counterflow, because yeah, sorry, I made a mistake here. It should not be this. 1 second. So inlet outlet temperatures are okay, but the U and A are not same. You just fix the and same heat transfer rate. So there, then your area requirement for which heat exchanger will require lesser area or cost. So typically your LMTD for counterflow heat exchanger is higher than your 1 second. And you know, since Q is nothing but UA delta T LMTD, and we are keeping Q as constant, therefore, and U also as constant, in that case your typically area required for counterflow heat exchanger is lesser than the area required for parallel flow heat exchanger. If sometimes it is mentioned that overall heat transfer area is not, overall heat transfer coefficient is not constant, then this product of UA will be lesser than will be less for counterflow than parallel flow, and typically that UA comes into your number of transfer unit, NTU. NTU formula is UA by C minimum. So and this, the reason is what happens in counterflow, with with mass flow rate you can control the delta T between your hot fluid and cold fluid, and you can maintain sufficient delta T for heat transfer over the area of the heat transfer. But in parallel flow, since one fluid gets cold and one fluid gets heated, their delta T reduces typically as the length of the heat transfer tube increases. And even with the mass flow rate arrangement, it's not possible to control it up to that extent. Therefore, since for any heat transfer, temperature difference is the driving potential, that is more in counterflow as compared to parallel flow, and therefore typically this observation is achieved. So that's how you should explain, because in many interviews they ask this question, and in some exams also. Maybe I'll take one question here. They typically ask this. So it's very simple for a straightforward question, but you should know what is delta T, LMTD, and all those things. So we can take one problem. So they have not mentioned whether it's a parallel flow or counter flow heat exchanger. It's just that they have given you temperatures. So this is the temperature variation. It's not up to the scale, so don't worry about it. It's a schematic. So on x-axis you have, let's say, or maybe I should have done that. 1 second. Yeah, so this is your x-axis, your length of your heat exchanger. Okay, so maybe it is starting from this point. Okay, I should have drawn the lines first and then made the temperature profile, but anyway. So, and this is your length axis of your heat exchanger. So this fluid is getting heated. So this is your cold fluid, and this is your hot fluid. And it is mentioned that at the inlet, this THI is 210 degrees Celsius. At the outlet, it is unknown. The cold fluid temperature at the inlet is 40 degrees Celsius, and at the outlet it is 95 degrees Celsius. So it is given in the question. Mass flow rate for both hot and cold fluids is given as 0.125 kg per second. And it is mentioned that your specific heat capacity for your cold fluid is 4 to 100 joule per kg Kelvin, so it is water. And for hot fluid it is half of it. It is, I think, some sort of oil may be there, because typically oils will have lesser CH or C. And it is asked that what is the area ratio for counter flow and parallel flow heat exchanger operating under these conditions with same heat transfer rate. So it is just a application of what I just mentioned in the discussion. So here it is given that yeah, and also one thing, with same overall heat transfer coefficient. So this is actually a very general abstraction of the problem. In practice, it may not be possible to maintain same U and Q, but for the sake of problem solving, it is given like this, and that is not the point. The point is, uh, uh, in practical cases, it may be different, but the point that is conveyed here is assume that there is not much change in the U, and practically speaking, you can consider it as to be same order of magnitude or same value. In that case, what is the area requirement or area ratio? So we know that Q is nothing but QA, let's say counter flow into delta T LMTD, LMTD of counter flow heat exchanger, and these are same as parallel flow delta T LMTD for parallel flow rate. So to calculate LMTD temperatures difference, we need all 4 temperatures, otherwise we can't write. So here only 3 temperatures are known, 4th is unknown, and typically we use energy balance, assuming no losses to surroundings. You can apply energy balance. Overall energy balance gives, whatever heat is lost by hot fluid, which will be Thi minus Tho, that will be equal to the heat gained by the cold fluid, right? This is your overall energy balance. So here all the quantities are known, their mass flow rates are same, so m dot gets cancelled, and the inlet is 210 and the 4090. So CH is, one second, yeah, sorry. So here CH is 2100 and CC is 420, 4200. So then what happens? Let's say 2100 into this is 210 minus unknown quantity 4200, 95 minus 40. So you can see this is just twice of this, and the difference is 55 into 210. So therefore your THO will be 210 minus 110, and your outlet temperature of hot fluid will be 100 degrees Celsius. So this is first part, and typically in heat exchanger problems you have to employ energy balance everywhere. That is typically the first or key step, and then one second. And we need to find, one second. Yeah, so basically we need to find the area ratio, right? So area ratio of counter flow by parallel flow. This is what we have been asked, and that is equal to delta T LMTD for parallel flow and delta T LMTD for counter flow. And in the question that this variation is given, it is it is for parallel flow. Even though it was not mentioned clearly, you should know from the variation it is for parallel flow heat exchanger, right? So therefore, first you can calculate the delta T LMTD for parallel flow as delta T at inlet, delta T at outlet divided by logarithmic temperature, logarithmic ratio of the temperature differences. So what is delta Ti at the inlet? It is 210 minus 40. So 210 minus 40 minus at the outlet it is 100 minus 95 and divided by ln of those 210 minus 40 divided by 100 minus 95. So this is nothing but 170 minus 5. So 165 and ln 170 by 5. So ln 170, sorry, 165 divided by 165 divided by ln 170 divided by 5. So it is 46.79 degrees Celsius. And if it is a counter flow heat exchanger, the arrangement will look something like this. And let's say these are your inlet and outlet points along the length axis. So this will be your length axis and this is your temperature axis. In counter flow, it will be something like this, right? Where your hot fluid will again get cold. So your THI will be 290 degrees Celsius. Oh, sorry, 210. Your THO will be 100 degrees Celsius. We just calculated it. And your TCI, that is 40 degrees Celsius. And your TCO, that is 95 degrees Celsius. So this is your typical counter flow heat exchanger arrangement. Now here, if you calculate the delta T LMTD for counter flow arrangement, what is the difference at the inlet? It is 210 minus 95 minus what is the difference at the outlet? 100 minus 40, and then you have to take the logarithmic ratio of these two numbers. So it will be 95 divided by 100 minus 40. So what is it? 210 minus 95. It will be 115 minus 60 divided by ln 115 by 60. So this is 115 minus 60 is 115 minus 60. That will be 55, and then you have to divide it by ln 115 by 60. So that gives you 84.54 degrees Celsius. So you can clearly see here, your area ratio of counter flow to parallel flow will be nothing but 46.79 divided by 84.54, and that will be 46.79 84.54. So it is approximately 0.55 times. So basically, counterflow heat exchanger requires only 55% of the area required by the parallel flow heat exchanger. Don't look at these numbers because it may not be a practical case to implement this, but typically speaking, you need lesser surface area for counterflow heat exchanger as compared to parallel flow, assuming the heat transfer rate and temperatures are more or less similar. So that is one key takeaway. So that is there. Then then there are certain cases here which we should discuss. We'll take some problem, but because this NTU method, right? So in that case, what happens? There are different correlations. So this method, first of all, you should know when this method is used. When outlet temperatures of hot and cold fluids are not known. So if you don't know, because when you start to design a heat exchanger, you may know what inlet temperatures are there, but you will not know what are the outlet temperatures, and you cannot make and then see, okay, did we make it correctly or not. So in that case only this LMTD method is used, and very practically very widely used. So here, what is effectiveness? It is effectiveness is denoted by your epsilon symbol. It is Q actual divided by Q max, and Q actual, it can be defined based on your hot stream, or it can be defined based on your cold stream also. Both are okay. Whereas Q max, which is, you should remember this, it is important to note. So whichever MCP is minimum, that, and take the maximum temperature difference, which is typically between inlets of cold and, so this is your temperature, maximum temperature difference possible. So this is also very famous question. Sometimes in GATE directly this formula is asked, and people usually get confused with this. Typically what we think is to have maximum Q, we should have maximum delta T as well as maximum MCP. Delta T is maximum, fine, but MCP, if you have maximum, you will not get maximum delta T, because these two things are inversely related. So therefore you should have minimum MCP and maximum delta T. And then there are some correlations for what you say effectiveness in terms of NTU and this thing, capacity ratio. NTU is nothing but number of transfer units. NTU is nothing but UA by MC minimum, or here typically they write capital C for product of M dot and C. And there is one thing called as capacity ratio, typically denoted by capital C. One second. Yeah, so it is nothing but C min by C max. So C min is the product of MCP for minimum or lower the value of hot on cold, that MCP is taken at the numerator, and the higher value is taken at the denominator. And then you'll have for parallel heat exchanger, you have correlation for effectiveness in terms of as a function of NTU and capacity ratio, which is given as one minus exponential of minus NTU 1 plus C bracket close divided by 1 plus C. And for counterflow heat exchangers, the effectiveness is given as 1 minus exponential of minus NTU 1 minus C divided by 1 minus C into same term, exponential of minus NTU 1 minus C. You are expected to remember these two correlations. For other shell and tube and other plain type of heat exchangers, you may not remember the effectiveness formula, but at least for counterflow and heat exchangers, you should remember. And here there are two cases that you should remember. First case is if one of the fluids is undergoing a phase change. In that case, what happens? Your MCP, m dot Cp of phase change fluid, it becomes your Cmax, and that tends to very high value. And therefore your capacity ratio, which is Cmin by Cmax, it tends to 0 or very small value. And therefore your effectiveness formula, both of them, for parallel as well as counterflow, they all boil down to 1 minus exponential minus NTU. Same for parallel and counterflow heat exchangers. And this also has a very important takeaway, that heat exchanger arrangement does not matter. And what I mean by arrangement is parallel type or counterflow type, in case or it does not matter if one of the fluids undergoes phase change. So if you know that like let's say if it is a water condensing or water evaporating in boiler, etc., so there it doesn't matter whether it's parallel flow or counter flow, you'll get same effectiveness, because this correlation boils down to same formula for both. And there is second case, which is called as sometimes balanced heat exchangers. So what is balanced heat exchanger? In that case, your C is 1, your capacity ratio is 1, and what happens in that case is uh, you know so if it is a or for parallel heat exchanger with C equal to 1, in that case what happens to your effectiveness formula? it becomes 1 minus exponential minus 2 NTU divided by 2. So there is no problem here when you have C equal to 1. But for counterflow heat exchanger with C equal to 1, what happens to your effectiveness? In the numerator you have 1 minus exponential of 0, and in the denominator you have 1 minus again exponential of 0. So this is a 0 by 0 form. So you have to recall your mathematics calculus class. In such case we have to take the limit. So if we have to check if the limit exists. If it exists, then you can have some finite value for epsilon or effectiveness. If it doesn't, then you cannot use this formula, or you cannot predict effectiveness in this case. So what happens? Taking limit as C tends to 1, we can write epsilon as limit C tends to 1. What is your expression? It is 1 minus exponential minus NTU into 1 minus C divided by 1 minus C exponential minus NTU 1 minus C. So we know this is 0 by 0 form, right? So we have to take L'Hospital's, we have to apply L'Hospital's rule and then differentiate numerator as well as denominator. And if you do that, what you get is 1 is constant, so it goes away, and exponential difference is same. The differentiation of exponential power something is exponential power that thing into the differentiation of inside thing. So with respect to C we have to do, right? So NTU, because at minus NTU will get cancelled because it's a constant, it will be 0 differentiation, and then you'll have one term C NTU, that differentiation is NTU, and in the denominator again 1 will go because it's a constant. Then you have to do UV rule, UV differentiation of UV formula. So first simple, we'll just differentiate C and the other term remains as it is, and then you differentiate the other term. There will be one minus sign here, here, and here also, and you'll have exponential minus NTU, whatever is the denominator, you'll have same thing here also, minus C into NTU. So then you have to take this exponential term common. This term, it is common in all three all three cases or terms, and it gets cancelled. So what you are remaining here is NTU by 1 plus C NTU, and then you put C as 1 and you get NTU by 1 plus NTU. So this is a very famous formula and it is asked many times also, and this is only possible only for counter flow heat exchanger. So you should remember that. In parallel flow, even if C is 1, it doesn't matter. So therefore, when they call balanced heat exchanger, it also sometimes means they are talking about counter flow heat exchanger with C equal to 1. In some problems, they did not mention that whether it's counter flow or parallel flow. They'll just say that it is a balanced heat exchanger, and then you have to solve those problems. So there you should know that if nothing is mentioned, balanced heat exchanger is nothing but a counter flow heat exchanger with C equal to 1, capacity ratio of 1. Okay, so that is as far as this thing goes. One more thing that I wanted to see, or one small derivation is there, so it can be taken as third note. So you have this delta T LMTD as delta T at the inlet minus delta T at the outlet, and then you have the logarithmic ratio of those two, right? So, but there will be one case. One second. Yeah, I mean, in the same case. What happens with this counterflow heat exchanger with C equal to 1? That means capacity ratio is 1. That means m dot Cp of hot fluid is equal to m dot Cp of cold fluid, right? So in that case, so what it means is your m dot C for hot and m dot C for your cold fluids are same. That means your THI minus THO is same as TCO minus TCI, because Q is same, right? So from there you get this. And this also means if you just rearrange the terms, it means THI minus TCO is equal to THO minus TCI. And this THI minus TCO is nothing but your delta T at inlet and delta T at outlet, THO minus TCI. So you have this particular case when your counterflow heat exchanger has capacity ratio of 1, then your temperature difference at inlet and temperature difference at outlet are same. And what happens to LMTD in that case? Uh, this will be same, right? So it will be 0 divided by ln of 1, which is also 0. So again, this is a 0 by 0 form. So how do you calculate your logarithmic temperature difference, logarithmic mean temperature difference in case of counterflow heat exchangers with C equal to 1? So here also you have to take LMTD, limits. But before that, you need to do slight modification. So what you do is you take delta TO as the common common from the numerator. So what you end up with, delta Ti by delta To minus 1 in the numerator, and denominator remains as it is. And the reason why we do it is because we want to do a substitution. So then what you do is put delta Ti by delta To as some variable x, and then your LMTD becomes some constant of delta To into x minus 1 divided by ln of x, right? So we know that this is a 0 by 0 form. So we apply limits, and delta To is constant because it's a steady state problem. Then what happens? This is equivalent to seeing if your x approaches 1, what is the limit? If limit exists, then you will have some value for logarithmic mean temperature difference. Otherwise, it doesn't exist, mathematically speaking. So we have to use L'Hospital rule again. Here also I should have written, right, by L'Hospital's rule. Here also using L'Hospital rule. What you get? You have to differentiate the numerator, which will be 1, as well as the denominator, which will be 1 by x. And then you put x as 1. So what happens? It becomes delta TO and 1. Therefore, your logarithmic mean temperature difference is nothing but equal to delta TO, which is nothing but equal to delta TI, which we already saw, right? Here. So therefore, you end up with a condition which says that your mean logarithmic temperature difference is nothing but equal to your temperature difference at the inlet as well as at the outlet. And what it means is, the temperature difference remains constant throughout the length of your heat transfer tubes or pipes. So at any cross section, if you take the delta T, that will be equal to the delta T at the inlet as well as delta T at the outlet, as well as equal to the delta T LMTD. And that is a very special case. You should keep in mind that this is valid for this counterflow heat exchanger with C equal to 1 or capacity ratio equal to 1, which is also called as balanced heat exchanger. So for balanced heat exchangers, you need to keep in mind two things. One is that its effectiveness formula is different, or it is calculated after using limits, and also its LMTD formula is also simplified. And in case of phase change wala heat exchanger, it doesn't matter whether it's parallel or counter. The effectiveness formula is boiled down to the same correlation for both of them. So if you remember all these three notes as well as the previous discussions, I think you should be able to solve all those all the numerical problems that you'll face. And again, one thing is there, one small thing which is called as correction factor. So typically it is represented by F. Don't get confused with the shape factor that we studied in the radiation part, which is also represented by F. So here correction factor is typically delta T LMTD for current configuration divided by delta T LMTD for counterflow configuration with same temperatures. So see, in parallel and counterflow, you have direct correlation for delta T LMTD. But in reality, heat exchangers may be of various configurations such as shell and tube, compact, and in there also there will be some subcategories, like multi-pass, multi-shell, and in plate type fins also, plate type heat exchangers also there will be counterflow or cross flow or something like that. So you cannot define LMTD for every configuration. So what is typically done is they, with the configuration of heat exchanger that is under observation, typically correction factor is also given. So what it means is, as compared to a cross flow heat exchanger with these inlet and outlet temperatures, whatever is the delta, whatever is the LMTD, you multiply that LMTD with some correction factor and you will get the LMTD for present current configuration. So it is a simplification. One simplification also is done using this. So you should remember that also. And apart from that, I think most of the things are easy. We'll take some simple problems now. Maybe previous year GATE questions also we'll take. One second. Yeah, so and sometimes they ask 1 mark question which is directly straightforward. So in this question, which is a previous year gate question, it is mentioned that uh, hot fluid enters at 76 degrees Celsius and leaves the heat exchanger at 47 degrees Celsius. And similarly, cold fluid also enters at 28 degrees Celsius and leaves at 55 degrees Celsius. So all 4 temperatures are given. And it is uh, the capacity ratio is 1. Then what is the effectiveness of this heat exchanger? So it is mentioned that capacity ratio is 1. So therefore C equal to 1. That implies C min or C max both are equal. So that will be some, let's say, C. So we know that effectiveness is nothing but Q by Q max, right? So Q can be defined in terms of hot fluid as well as cold fluid. Let's say we'll take in terms of hot fluid. So whatever heat it loses actually, and divided by Q max is nothing but C min into delta T max, right? But here this C min and C are equal, so these two go away, and in the numerator you have THI minus THO. Okay. So what will be your T max? It will be THI minus TCI. So therefore you have all 4 temperatures here. 76 minus 47 divided by 76 minus 28. So 76 minus 47, it will be 29, and 76 minus 28 will be 48. And if you take the ratio, it comes out to be 0.604. So that is 60.4% of effectiveness. So this type of questions are also there, where you must know the definition of effectiveness and what it represents, etc. If you know that, you can solve these questions maybe in a few minutes. So that is there. Other than that, what else is there? One second, let me see. Okay, so this is thoda different variety of question. Again, gate question. So here it is mentioned that hot oil is cooled from 80 degrees Celsius to 50 degrees Celsius in an oil cooler which uses air as a coolant. The air temperature rises from 30 degrees Celsius to 40 degrees Celsius in the process. The designer uses LMTD value of 26 degrees Celsius. Then type of heat exchanger is. So you have 4 options: parallel flow, you have double pipe, counter flow, and cross flow. So actually this was 2 marks question in 2005 gate, but it's difficult. I mean, in exam, so you have to see. It can be either this parallel, counter, or cross, because double pipe is it's basically parallel and counter flow and cross flow. Everything is double pipe. So B is not the correct option. So out of these 3, you have to see. So what you can do is you can just calculate delta T LMTD for parallel flow. So in parallel flow, it will look something like this, the temperature profile, something like this, right? And it is cooling from 80 to 50 oil. This is your air, which is getting heated from 30 to 40. So now your LMTD will be delta T at the inlet is 50 minus 10 ln 5 by 1 or 50 by 10, whatever you want. So basically it is 40 by ln 5. Then if you do that, you should get 24.85. Okay. And similarly, you can calculate for counter flow. And what will that be? In counter flow, it will look something like this. Right. So this will be your oil. This will be your air. Same temperatures will have 30 degrees Celsius, and this will be your 40. So now your delta T at inlet is 40, and at the outlet it is 20, and you'll have ln 40 by 20. So basically ln2. So 20 by ln2. And if you do that calculation, you'll get it as 28.85 degrees Celsius. And now in the question it is mentioned that the designer is using 26 degrees Celsius as the LMTD. If it is assumed as parallel, then it is 24 point something. If it is assumed as a counter flow, it is 28.85. So you cannot assume parallel flow because then your LMTD is lesser, right? See, in designing, you can assume anything which is less than actual, or let's say actual heat exchanger is giving you LMTD of 30 degrees, but you are assuming at 26, then it is okay. But if your actual LMTD is 20 and you are assuming it at 26, then it is wrong design. So therefore, you cannot assume it as parallel flow. Okay, so now we have another option which is whether it is counter flow or cross flow. And as I said, if it is a cross flow, they should have mentioned some correction factor. They have not mentioned any correction factor, so you cannot assume it as a cross flow, because again, if I give you correction factor of 0.1, then your LMTD will just become as 2.8 there, and that is again wrong. So therefore counter flow heat exchanger is the conservative choice. So it's not just calculating, it's about using that information to solve the question is also important. So here it should be, the C option should be correct, which is counter flow, because parallel flow is giving lesser LMTD, and cross flow there is no correction factor mentioned, so you cannot assume it arbitrarily. Okay, so let me just see if any other type of question is there. Yeah, I mean, another objective questions are not that tough. Yeah, maybe we can take one question on the okay. So this is again a great question. So in this question it is mentioned that a balanced counterflow heat exchanger has surface area of 20 meters square and overall heat transfer coefficient U as 20 watt per meter square Kelvin. Air entering at 0.4 kg per second and 280 Kelvin with Cp of 1000 joule per kg Kelvin is to be preheated by the air leaving the system at 300 Kelvin, and it is asked that the temperature in Kelvin of the preheated air is, and it was a data entry question. So first hint is the keyword balanced. So we know that, see, there is like conventional way to solve this question. Like it's not like you should know, only that balanced question, balanced counter flow heat exchanger derivation, etc. But if you don't know, see, they have not mentioned at what mass flow rate the hot air is leaving. Or, 1 second. Yeah, here two things are unknown here. Uh, so maybe I'll draw the image for or the schematic first, because this is thoda tricky problem. It's not straightforward. So it's again it's a counter flow type of heat exchanger, something like this. Okay, and this is your length axis, this is your temperature axis. So there is a hot air, and again the air is heating air, so basically it's the same fluid, and air is entering at 0.4 kg per second and 280 Kelvin, and that is to be preheated. So this is your TCI is 280 Kelvin, because this is your cold air which needs to be heated, and your hot air which is leaving the system at 300 Kelvin. So this is your THO, which is 300 Kelvin. So THI is not given, and TCO is also not given. And TCO is, in fact, it is asked, what is TCO? So and what about the MCPs? CP will be same because it is air, and since it is balanced counter fluid exchanger, they have not mentioned the mass flow rate for another airstream, but it should be same only, right? Because then only you will have C equal to 1. So m dot C has to be same. So m dot will be same in both streams. So if you do that, we know that uh, for balanced counter flow heat exchanger, we know that delta Ti or delta T LMTD is equal to delta T at the inlet and delta T at the outlet. So we know delta T at the outlet, right? So this is 20 Kelvin. So that will be equal to delta T at inlet and LMTD also. That is one. Then we know that effectiveness is NTU by NTU plus 1. This also we did derivation. And NTU is nothing but UA by C minimum. Here C minimum, C maximum, everything is same. And U is given as 20, area is given as 20, and your mass flow rate is 0.4, and your CP is 1000. So this is your C min or C. So this is basically 400 by 400. So you have NTU as 1. And therefore your effectiveness is 1 by 1 plus 1. So this is 0.5. And you know, effectiveness is nothing but Q by Q max. And here, C min, everything is same, so only temperature differences will remember. So you can write it as THI minus THO divided by maximum temperature difference, that will be THI minus TCI, and this will be again equal to TCO minus TCI divided by THI minus TCI. Okay, so you take these two and equate. What you get is 0.5 is equal to THI is unknown, THO is known 300 divided by THI is unknown minus TCI is known, and we can take third thing also, no issues. TCO is unknown, TCI is 280, and the denominator is same, THI minus 280, right? So now from this you can solve for THI, right? Therefore your THI will be 0.5 minus, so 0.5 THI minus 140 is THI minus 300. Therefore your THI is nothing but 160 into 2, so 320 Kelvin. Okay, and now you put this THI into this formula. Therefore you have 0.5 equal to TCO minus 280 divided by THI is 320 minus 280. So this is 40 into 0.5 is 20. Therefore your TCO is 300 Kelvin. And this is what is asked. Okay. So this was one of the interesting problem. Now, yeah, I think we can go for some conventional problems. These were like simple problems, but in conventional problem it will be lengthy because it will involve, you know, various other things also. We'll see that. Just give me some time. Yeah, so this is a conventional question. So air with average inlet velocity of 10 meters per second at 300 Kelvin enters a copper tube of 11.2 mm diameter and 2.5 meter length. The tube wall is maintained at 373 Kelvin by condensing steam on it. So this is a heat exchanger with one of the fluids undergoing phase change. Using LMTD method, determine air outlet air outlet temperature, and you know, it is also mentioned that assume constant heat transfer coefficient and neglect tube wall resistance. So even these informations are given. In many questions this is also not mentioned, so typically we assume it. And now some air properties are also given. so that you can use them wherever required. So conductivity 0.02624 watt per meter Kelvin. Cp is given as 1.005 kilojoule per kg Kelvin. Density is 1.174 kg per meter cube. Kinematic viscosity is also given 1.568 10 to the power minus 5 meter square per second, and Prandtl number is given as 0.7. And additionally, two Nusselt number correlations are also given, 3.66 and Nusselt number 0.023, RE power 0.8, PR power 0.4. This is for Reynolds number less than 2300, and this is given for turbulent flow. So this is the all the data that is given. So now, before proceeding further, what we should do is we should at least draw the schematic. We can draw that, but before that, let's just see. Since they are asking us to use Nusselt number correlations, we'll first find out what is the Reynolds number. Okay. So Reynolds number will be rho Vd by mu. But here they have directly given you the kinematic viscosity, so you can use it this way. Velocity is given as 10, diameter is 11.2 mm divided by viscosity, kinematic viscosity is 1.568 10 to the power minus 5. So if you do this calculation, you should get Reynolds number of at least this order 7. And since this is greater than 2300, you'll have to use Nusselt number correlation, which is 7142 power 0.1. Prandtl number is given as 0.7, so no need to calculate it again. And this will be equal to your HDK, where HD is 11.2 into 10 to the power minus 3, since we are talking about SI units. And K is 0.02624. So from here you get the heat transfer coefficient as, let me do the calculation. So yeah, we have 0.023 into 7142 raised to 2.8 into 0.7 raised to 0.4 into 0.02624, and you need to divide by 11.2 into 10 to the power minus 3. So you get H as 56.57 watt per meter square Kelvin. Okay. Now let's see what is there. And since they have not mentioned any outside heat transfer coefficients, etc., second H by K. Yeah. So so this will become your overall heat transfer coefficient, because they have not mentioned any outside heat transfer coefficient correlation, etc. So you can assume that whatever is your inside heat transfer coefficient, it is same as your overall heat transfer coefficient. And then you can draw the schematic of your system. So there is a hot fluid which is your steam, which is condensing, so its temperature remains same. So that is one part, because phase change is typically assumed as a constant temperature process. And then you'll have a cold fluid which is getting heated. So this will be your THI. Actually it doesn't matter, but let's say for the sake of things, we mention it as it is. Let's say this is your direction of flow for steam. So this at 370, sorry, this is 373 Kelvin. Inlet is 300 Kelvin. Outlet is to be found out. Okay, what else? Yeah, so basically your delta T LMTD, it will be nothing but 373 minus 300, so that will be 73 is the delta T at the inlet. At the outlet it is 373 minus TCO, which is unknown, divided by ln 73 by 373 minus TCO. You can simplify further. So this will become TCO minus 300 at the numerator, and you will have ln 73 by 373 minus TCO. So by the looks of it, your TCO should be greater than 300. That is first observation. Yeah, so that is one thing. What else is there? So now we know that Q is nothing but UA delta T LMTD, right? And this is your surface area, overall surface area. So that is one thing. This will be again equal to the m dot air or m dot Cp into air into TCO minus TCI. Okay. So now we don't know m dot. M dot of air is nothing but rho A P. AC is cross sectional area. So density is given 1.174 into cross sectional area will be pi by 4 into t square. So 11.2 into 10 to the power minus 3 cos square into velocity, which is 10. Okay. So if you do this calculation, you should get 1.157 into 10 to the power minus 3 kg per second. Okay. Now that is your area. It looks fine only because minus 6 minus 5. 1 second, I'll just check. 11.2. 1.174 into pi into 10 into 11.2 square into 10 to the power minus 6 divided by 4. Yeah, so 1.156. So that is your m dot. Cp is also given. Now coming back to this side, this UA LMTD. U we already calculated, which is 56. A is the surface area for heat transfer. So what is the AS? AS will be pi d into L. Pi d L, right? Because that is where the heat transfer is taking place. So that will be pi into 11.2 into 10 to the power minus 3, and length is also given, right? Length is given as 2.5 meters. So if you multiply these things, you should get pi 2 to the power minus 3 into 2.5. So this comes out to be 0.087 or 88 meters. That is, so now we have everything, and we can plug all these things in equation 1. So therefore equation 1 becomes, so your U is 56.57, area is 0.088, LMTD is TCO minus 300 divided by ln 73 by 373 minus TCO, that is equal to m dot Cp air. M dot is 1.157 into 10 to the power minus 3. Cp of air is 0.005 into delta T. So this is TCO minus 300. So you can observe, oh my god, this brackets gets cancelled. Now we have one equation and one unknown. And what is that? So therefore you have ln 73 by 373 minus TO. Maybe I should put it in the bracket. Is nothing but 56.57 into 0.088 divided by 1005 into 1. Or maybe, okay, 1.157 into 10 to the power minus 3. Okay. So what is this? 56.57 into 0.088 divided by 1005 into 1.157 into 10 to the power minus 3. So this ratio is 4.281. So e to the power 4.281. Therefore you have 73 by 373 minus TCO equal to 72.313. One second. So 73 divided by 72.313 will be this. So TC will be minus 373. So TCO is approximately 372 Kelvin. Okay, 1 second. Does this make any sense? It can happen. It's not like impossible event. The only thing that I'm worried about is whether we have calculated H correctly. But other than that, everything is fine. So let me just do it once. Zero point 0.02624 divided by 11.2 to 10 to the power -3. Yeah, so I think it's correct. So you can observe that uh, the steam is condensing at 373, and your outlet temperature of your cold or whatever this air is, it almost reaches to 372. So the effectiveness, if you calculate, it should be pretty good. So that is one type of problem. Maybe we can take one more problem. I'm not sure whether we'll be able to finish it in time, but let's see. So yeah, so we'll take one problem and we'll stop. So this is also similar problem. Again, condenser unit, condenser as the heat exchanger unit, but it's more involved. So find surface area required for a condenser handling 25,000 kg per hour of saturated steam at 0.5 bar. The temperature of condensing water is 25 degrees Celsius. So this, in condenser, water is condensing at 25,000 kg per hour rate and at temperature of 25 degrees Celsius. The cooling water is heated from 15 degrees Celsius to 25 degrees Celsius. So whatever is the cooling water circulated through the condenser, it gets heated. Assume overall heat transfer coefficient of 10 kilowatt per meter square Kelvin. The condenser has 2 water passes with tubes of 19 mm OD and 1.2 mm thickness. find the length of tubes and number of tubes per pass. Assume velocity of water as 1 meter per second. Correction factor is given as 0.86. At 0.5 bar, saturation temperature is 32.55 degrees Celsius, and HFG, which is latent heat of condensation, is given as 2560 kilojoule per Kelvin kg. Cp of water is 4.2 or 4.18 kilojoule per kg Kelvin, and density of water is given as 1000 kg per meter cube. So this is again a similar variation of the problem, but here you need not calculate U because it is given in the problem. So last time we used Nusselt number, correlation, etc. for that. Here that is given. It's like dealing with more dimensions and sizing of the heat exchangers, tubes, etc. So this is the second variation of these kind of problems. And how we do this is same. Here you have a sorry. Yeah, so again here, let's say if this is your total length of your tubes, then you have a condensing fluid, which is steam. But here you should know one catch is there. They have mentioned that the condensation is happening at 25 degrees Celsius, but the saturation temperature corresponding to 0.5 bar is 32.55 degrees. So that means the steam is not saturated steam or saturated water when it condenses. It is subcooled water. So that is also one important thing you should notice. So temperature will be same only. What you say? Temperature will not be same as throughout, right? Because during phase change it will be 32.55. But what will happen by the end of the what you say? By the end of your should I say that? Yeah, so this will not be a straight line is what I'm trying to say, because temperature initially or at the start till the phase change is happening, the temperature will be constant of 32.55. So this will be your 32.55 degrees Celsius because that is the saturation pressure. But what happens somewhere in between, your steam gets into the subcooled region. It condenses as a water and then gets cooled. So then there will be a temperature drop. I'm sorry. So there will be a slight temperature drop like this. And you'll end up at the temperature which is 25 degrees Celsius. So another question can be formed is at what length this happens, but this is not asked in question, and that is some other information also is required. So this is your subcooled liquid water. Okay. And then you have a cooling water, which is going from 15 to 25. So basically, uh, this guy also goes from, so like this. So this is your cooling water. So this also comes in at, so TCI is 15 degrees Celsius, and this is your TCO as well as THO, and your THI will be 32.55. Okay. So like this it is there. So now, first of all, you need to calculate, how much water is flowing and all those things. So let's see what all things are known here. So we can calculate LMTD because all four temperatures are known. So first do that. LMTD will be 32.55 minus 15. So at the inlet it will be 17.55, and at the outlet it is 0, right? One second. Uh, hmm. Yeah, I think here it is not like this. The arrangement is because uh, it looks suspicious, right? Yeah, and it cannot be like this because if you do that arrangement, let's say if you arrange like this, then you have LMTD in which you know you'll have ln 17.55 divided by 0, and that is not possible, right? Because this is not defined ln of infinity. So in that case, the arrangement is not as same as what we have assumed here. So it will be counterflow. Here I assumed it as parallel flow because nothing was mentioned in the question, and therefore it should not be like this. Otherwise, you'll not get any practical value of your LMTD. So, array. So it will be something like this. Yeah. So this is your THO. Your TCI will be 15, and then your TCO will be 25. And this is your cooling water. So counterflow arrangement will be there. Parallel is not possible. So if you do that way, then what is your LMTD now? So 32 minus 25. So that is 7.55 at the inlet minus 25 minus 10. So 10 at the outlet divided by ln 7.55 divided by 10. So if you do this, you should get 8.72 degrees Celsius. So see that this is also one hidden thing that we did not observe initially. Now we have U, A is unknown, and delta T LMTD is there. But see, we know that Q is U, A, delta T LMTD. So here we have this guy and this guy. This is unknown. But this is also unknown, right? Q. So how do we find Q? Q can be calculated as heat lost by steam, or it can be heat gained by cooling water, right? So what is the heat lost by steam? Because for steam we have m dot steam into HFG plus Cp of steam into delta T of subcooling, right? Because for certain part it was a phase change, and then it is a sensible cooling of the condensed water. So m dot steam was also given, which was 25,000 per hour, kg per hour. So you need to divide with this thing, you will get in kg per second. Then you have 2560 into 10 to the power 3. This is your HFG plus Cp of, it will not be steam, sorry, it will be water because it is a condensed liquid now. So that is 4.18 into 10 to the power 3 into 32.55 minus 25. So that is the degree of subcooling. So if you do these calculations, you should get 17.99 into 10 to the power 6 watts. So this is one important observation. So now you can use this in the main energy balance, right? This equation 1. Okay. Yeah, and one thing we missed here is the correction factor, because it is not a counter fluid exchanger. So it is something like cross fluid exchanger, right? So that this LMTD is assuming cross flow, but in reality it is not. It is somewhere in between cross flow. So therefore they have given a correction factor. So that also you have to multiply. So either you multiply LMTD here, or you can multiply at the Q level, whatever it is, you can do anyway, which is convenient. But this is again equal to heat gained by cooling water, right? And the reason why I'm comparing this is because we need to find how much, like how many number of tubes are required, right? So that depends on cross-sectional area of tubes and how much mass flow rate is going through those tubes, because anyway we have to pump the cooling water, right? So therefore this Q, which is 17.99 into 10 to the power 6, is also equal to your cooling water, or m dot of water, into Cp of water into 25 minus 15, right? And this is 4.18 into 10 to the power 3. So from here you get m dot of cooling water as 430.55 kg per second. So you can see how large this quantity is. So this is a practical example of a cooling tower or something like that in power plant. So now for a single tube, what is m dot that can go through it is rho a v. Density of water is given as 1000. Cross sectional area is given as, now we need the inner diameter, right? In the question they have mentioned that outer diameter is 19 and thickness is 1.2. So you have to subtract 19 minus 2.4, right, to get the ID. So this will be 19 minus 2 into 1.2 mm, so into 10 to the power minus 3, and velocity is given as 1 meter per second. So you multiply it by 1. Okay. So if you do that, you should get 1 second. Yeah. So what do we get? See, this 1000 and 10 to the power minus 3 goes away. I mean, they cancel each other. And then you are end up with the 14 minus 2.4 will be 16.6. 16.6 into shift pi, oh sorry, pi divided by this. So Yeah, velocity is 1, right? Yes. So this is rho AV. Oh, there will be one square, sorry. So there will be square, so this will be -6. So yeah, -3 will still be there. So 16.6 into pi. So there will be 16.6 square into pi into 10 to the power -3 divided by 4. Yeah. So you get 0.216 kg per second. So this is a mass flow rate through a single tube. Therefore, number of tubes required is nothing but 430, which is total mass flow rate of water required, divided by in each tube how much can go. So if you do this, you should get 430.55 divided by 0.216. So you get 1994 tubes. So you need almost 2000 tubes. So that is one thing. I mean, this number is like exactly like 93.28. So you have to round it off to the next higher digit. So that is 1994. So this is one part that you need this many tubes. Now we need to calculate the length per pass also, right? Because number of tubes we calculated, but we need to calculate what is the length per pass. So there are two passes. So whatever length you get, you have to divide by 2 so that you'll have a length per pass of that much. So basically, if you require 5 or 10 meters length, you may not have that in practical case. So what they do is they bend the tubes and they make them go again through the condenser. So that is how they reduce the length, but the cross-sectional area increases, something like that. So for that, you have to use the other condition, which is this, because here your area is coming into picture, right? So we know that Q is F A U into delta T LMTD. Delta T LMTD, U, everything is known, A is unknown. Therefore, A, which is your surface area, will be F U delta T LMTD. So we can calculate that. Your Q is 17.99 into 10 to the power 6 watts divided by your correction factor is 0.86 into overall heat transfer coefficient is 10 kilowatt. So that is 10,000 into delta T LMTD. So delta T LMTD was 8.72. So your area is 239.89 meters square. So that is total area for the tubes. And we know there are 1994 tubes, right? Therefore, surface area per tube or required surface area per tube is 239.89 divided by 1994. So divided by 1994. So that is 0.1203 meters square. Now area per tube will be nothing but equal to pi d O into L, right? DO is outer diameter. Therefore, length per tube, which is L, will be 0.1203 divided by pi into 19 mm, right? So you have to divide by this. So 0.1203 divided by pi pi into 19 and 10 to the power 3. So you get 2.015 meter. So this much length per tube is required. But there are 2 passes per tube. So therefore, length of tube per pass is nothing but 2.015 divided by 2. That will be 1.008 meters. And this is your final answer. So you need 1 meter of length of the tubes, and you need some 1994 tubes. So this is how you do the sizing and designing of the reactor. So maybe I can bracket this. What happened? Yeah, the number of tubes. Okay, so we are already at 8:10. So we'll stop now. And hopefully this course or my, this weekly discussion may help somebody. That's the hope. And with that, I conclude this class as well as this course from my side. Thank you everyone for attending, and hope this information finds some usefulness to you later. Okay, so thank you, and see you next time somewhere. Okay.